Welcome, everyone, to The Explainer. So, if you're an engineering student currently staring down the barrel of your Mathematics 1 analysis exam, take a deep breath. Seriously, consider this your friendly but highly rigorous exam survival guide. Today, we're completely cracking the code on sequences, series, and those notoriously tricky convergence criteria. We're going to take all that abstract math floating around your lecture notes and turn it into a structured, really practical toolset that you can actually use when the clock is ticking during your finals.
Here is the game plan for today's explainer. First, infinite sums, finite results. Second, partial sums and geometric series. Third, comparison test versus ratio test. Fourth, a calculation example using the ratio test. And finally, some exam tips and engineering applications.
All right, kicking things off with part 1, infinite sums, finite results.
Okay, let's just dive right in, shall we? It is time to completely rewire how we think about infinity. I want to pose a question to you that honestly seems totally counterintuitive at first glance. If I give you an endless, literal infinite list of positive numbers, and you add them all up, one after another forever, is there any way you can ever get a finite result? Your gut instinct is probably screaming that adding forever must eventually equal infinity, right? But mathematically?
The answer is a resounding yes. Sometimes you get a neat finite number, and sometimes, it blows up to infinity. And figuring out which one happens? Well, that is exactly what convergence tests are for. And listen, as an engineer, you aren't just doing this to pass a math class. Understanding whether an infinite accumulation levels off or grows without bound is literally the fundamental difference between a structure safely absorbing infinite load cycles and one that fails catastrophically because of cumulative material fatigue. It's structural dynamics hidden inside pure math.
Moving right along to Section 2, Partial Sums and Geometric Series. Let's look at how this builds our mathematical baseline. We need to formalize how we actually calculate these infinite accumulations. Because, let's face it, we're humans, and we can't literally sit at a desk and add numbers until the end of time. So we use what's called partial sums. Think of a series as a sequence formed by step-by-step addition. You start with the first term, S1, which is just A1. Then S2 is A1 plus A2. You just keep going until you hit a generic point. Let's call it Sm, which is the sum of all terms up to m. To find out what happens at infinity, we just take the limit of that partial sum Sm as m approaches infinity. If that limit exists and is a solid, actual number, we say the series converges. If it shoots off to infinity, it diverges. And this brilliantly illustrates our first really major tool, the geometric series. You are going to see this everywhere. It's simply the sum of a base number, q, raised to the power of n. Now, the incredible thing about the geometric series is that we know exactly how it behaves. It converges beautifully to the precise value of 1 divided by 1 minus q, but, and this is a massive but, only if it obeys the absolute golden rule of convergence. The absolute value of q must be strictly less than 1. If q is 1 or bigger, the whole thing diverges. Lock this rule in your mind right now. It is a foundational baseline for your exam.
Okay, Section 3. Comparison test versus ratio test.
Now, geometric series are great, but let's be real. In your exam, your professor's going to throw much uglier series at you. And that brings us to your core mathematical arsenal. You generally have two heavy hitters to attack an unknown series. On one hand, we have the comparison test, or Convergence Criteria. Think of this as an external check. You look at your ugly series and you try to find a simpler known series that is always larger than it. If the larger series converges, meaning it has a solid ceiling, then your smaller series is physically trapped underneath it and absolutely must also converge. On the other hand, we have the ratio test, or quotient criterion. This is more of an internal check. Instead of looking outside for a comparison, you compare the series to itself. You take the next term in the series, a sub n plus 1, divide it by the current term, a sub n, take the absolute value, and find the limit as n goes to infinity.
Now the ratio test is going to spit out a limit, and let's just call it q. And the rules here are super strict. If q is strictly less than 1, victory, your series is absolutely convergent. If q is greater than 1, the series is divergent. But look really closely at that third point. If q equals exactly 1, no decision is possible. The test completely fails. Guys, this is a classic exam trap. If you calculate q equals 1, you have to abandon the ratio test immediately and try something else, because the series could either converge or diverge.
But what's really interesting here is this specific snippet, straight from the professor's handwritten lecture notes. This is an absolute goldmine. It says, merke, or remember, if factorials appear in a sub n, the ratio test is usually the best choice. When you're sitting there sweating over a high-pressure exam paper and you see an exclamation mark representing a factorial, do not panic. Just immediately deploy the ratio test.
Moving to Section 4. Calculation example, the ratio test.
Welcome to the boss fight of this explainer. We're going to walk step by step through a full calculation, exactly like you'll need to do on exam day. Here is the strict 4-step methodology you need to write out to get maximum partial points. Step 1, write down the base term a sub n, and then carefully write out the next term a sub n plus 1 by replacing every single n with an n plus 1. Step 2, form your massive fraction, the absolute quotient. Step 3, flex those algebra skills to simplify and calculate the limit as n approaches infinity. And Step 4, state your final conclusion based on whether the result is less than or greater than 1.
Let's actually see this in action using example 9.16 from the source materials. The general series here is x to the power of n divided by n factorial. X could be any number, say 2, giving us 2 to the n over n factorial. We see a factorial, so our alarm bells are ringing, right? Use the ratio test. We set up our quotient. We have the n plus 1 term on top, which is x to the n plus 1 divided by n plus 1 factorial. And we divide that whole thing by the base term, x to the n over n factorial. Now, dividing by a fraction is the exact same as multiplying by its reciprocal. So the n factorial flips to the top, and the x to the n goes to the bottom. And here is where the magic happens. The factorials cancel each other out so beautifully. N plus 1 factorial is really just n plus 1 multiplied by n factorial. So the n factorials on the top and bottom completely vanish, leaving just an n plus 1 in the denominator. The x to the n plus 1 divided by x to the n. That just leaves a single x in the numerator.
So, what are we left with? We just need to compute the limit as n approaches infinity of the absolute value of x multiplied by 1 over n plus 1. Well, as n gets infinitely massive, that fraction 1 over n plus 1 shrinks down to exactly 0. And 0 multiplied by any finite number x is just 0. So our limit q is 0. Because 0 is strictly less than 1, we literally just proved that this series is absolutely convergent for every single real number x out there. Oh, and a really fun fact from the lecture notes? This specific, incredibly stable series is actually the mathematical definition of the exponential e function. How cool is that?
And finally, Section 5, Exam Tips and Engineering Application.
We have covered a ton of ground, so consider this your ultimate exam cheat sheet and our reality check. Look, under the immense time pressure of an exam, you just don't have time to try 3 different tests on one problem. You need to memorize this rapid-fire decision matrix. If you see factorials, the n with the exclamation mark, immediately use the ratio test, because as we just saw, the terms will neatly cancel out. If the series looks suspiciously similar to a simple harmonic or geometric series, deploy the comparison test. It's going to be super easy to set up a strict upper bound. And here's a bonus one straight from your lectures. If the entire term is raised to a power of n, like n to the power of n, use the root test, or Verzal criterion. Taking the nth root will instantly nuke that complex exponent and make your life so much easier.
So, what does this all mean? Why are you being tortured with abstract limits and these wild proofs? Let's bring it back to the physical world for a second. When you're out there modeling vibrations on a suspension bridge or calculating thermal stress in a massive engine block, those systems experience repeating load cycles. To predict their long-term behavior, you literally model those cycles as infinite series. If your math tells you the series converges, your design is safe, the stress level's out. If the math says it diverges, well, your bridge shakes itself apart. Passing this math exam isn't just some academic hurdle. It is literally the very first step in gaining the tools to prevent real-world engineering failures. So the next time you're sitting there setting up a ratio test, ask yourself, is my design converging to safety or diverging into disaster? Good luck studying, you've got this, and I'll catch you on the next explainer.